Yeah, so in the previous example we have seen that we wanted to divide a network into 4 parts where all the parts were of same size, right? So we did this. In previous example we had taken one network and we divided into half first, and size of each part is same, equal, right? And then we divided it into 4 parts, and again the size of each part was same, right? So if you remember, we got 64 IP addresses in each part. Now let us say I want to divide the network into 4 parts, but then my requirement is different. In the sense, I want to divide into maybe not 4 parts, 3 parts like this. I want to divide a network into 3 parts in such a way that one part will get 128 addresses, and other part will get 64, and the other part will get 64, right? So if I do such a kind of subnetting where the subnet sizes are different, it is called variable length subnet masking, VLSM. The reason is, whenever the size of the subnets are different, every subnet is going to get a different subnet mask. That is why it is called variable subnet. Okay, so let's see one example here. So let's take the same network 200.1.2.0. so this is the network ID, and this network I want to divide into 3 parts in such a way that first part will contain 128, second part 64, and third part 64. First of all, do we have these many IP addresses in the network put together? Yes. 64 plus 64 is 128, 128 plus 128 is 256. We definitely have these many IP addresses required in our network. Now the thing is, how are you going to divide them in such a way that one part will get 128 and the other part will get 64 and 64. So one thing you can observe like this. One thing is, how many bits do we have in host ID part? 8 bits, right? So let us say these are the 8 bits in host ID part. Now if I want 3 subnets, how many bits should I choose from the host ID part? In general, if you choose 1 bit, we are getting 2 subnets. If I choose 2 bits, we are getting 4 subnets. Here I wanted 3 subnets, therefore I need at least 2 bits. I need to choose at least 2 bits in order to get 3 subnets. In fact, we get 4 subnets here, right? If I choose 2 bits, I get 4 subnets, and the size of each subnet is, actually there are 60 bits, 6 bits remaining in the host ID part. Therefore size of each subnet is going to be 2 power 6, which is nothing but 64 IP addresses. But then this is not what I wanted. What I wanted is only 3 subnets, and each subnet size should be 128, 64 and 64. Therefore this kind of organization or this kind of arrangement is not going to work. We should think about some other methods. One method is this. The way we classified class A, class B, class C, class D addresses, the same way we could do here. So what I could do is, initially I'll choose first bit in the 8 bits, I'll choose 1 bit. Whenever I choose 1 bit, I am dividing the entire IP addresses into 2 parts. One part will contain 0 in that part, and other part will contain 1, isn't it? Now in the remaining half, wherever there was 1 bit chosen as 1, I'll choose the second bit in such a way that the second bit will be 0 for one subnet and the second bit will be 1 for the other subnet, right? Now if you look at this one, the subnet ID is going to be 0, and how many bits are remaining for the is 7 bits. So since 7 bits are remaining, 2 power 7, 128 addresses are possible here. And how many bits are remaining in the host ID part? 6 bits. Since 6 bits are remaining, 2 power 6, 64 is possible, and here also 6 bits are remaining, therefore 2 power 6, 64 bits or 64 IP addresses are possible. This is one way to do it. So if you follow this method, what is the subnet ID of this subnet? Subnet ID is always the first IP address, right? So in this subnet, if you see, it is going to be 200.1.2.1, 2, 3, 4, 5, 6, 7, 8. First one is going to be 0. First bit you have already fixed it as 0. So now you get from all zeros 7 zeros to 7 ones. So if you look at that, it is going to be 200.1.2.0 is the first IP address, and 200.1.2.127 is the last IP address, and totally we got 128 IP addresses, out of which the first IP address is nothing but the subnet ID of this subnet. right? And now if you look at this subnet, the next one, so it is 200.1.2.1234567 first two bits are fixed as 10, and how many bits are remaining? 6 bits, and these 6 bits can run from all zeros to all ones, right? Now the first IP address is nothing but 200.1.2.1 followed by 7 zeros, which is 128, and the last IP address is nothing but 200.1.2.128 plus 63, which is 191. Therefore this IP address 128 is the subnet ID of this second network, and the directed broadcast address for this network is 191, and the directed broadcast address for the first network is 127, right? So now this one, for the next subnet, we are going to again have the same way, 200.1.2.1234567 and the first two bits are going to be 11, and the remaining 6 bits can run from all zeros to all ones, 1 2 3 4 5 6, all zeros to 1 2 3 4 5 6. So this is nothing but 200.1.2.192, and this is nothing but 200.1.2.255. Therefore this one is nothing but the subnet ID of this network, and this address is the directed broadcast address of the third network. Therefore we got 3 networks and the subnet IDs and the required sizes. Now my question is this the only answer possible, or is there any other answer also? And before going to that, let us see about the subnet mask also. So what about the subnet mask? Subnet mask contains all ones in the network ID part and host ID part. So coming to this network, already we have 24 bits in the network ID part, and then 1 bit in the subnet ID part, and again 7 bits in the host ID part, right? Therefore this network has 24 ones, which means 255.255.255 dot followed by 1 bit is chosen for subnet ID part. Therefore if I choose 1 bit and all the remaining bits are zeros, it is going to be 128. Therefore for this subnet, this is the network ID and this is the subnet mask, right? And coming to this subnet, already 24 bits are there in the network ID part, and I have chosen 2 bits for the network ID, subnet ID, and the 6 bits are there for the host ID part. Therefore for the first 24 bits we are going to have 24 ones, which means 255.255.255 dot. In the host ID part, only 2 bits are chosen for subnet ID part. Therefore in those 2 bits, if I write 1, we are going to get 192, and the remaining 6 bits are going to be zeros, which means this is the subnet mask and this is the network ID, right? And for the third one, this one, again the same thing applies. Subnet mask is nothing but how many bits did we choose for subnet ID? 2 bits. Therefore subnet mask is already 24 bits are there in the network ID part, along with the 2 bits are there in the subnet ID part. Therefore even for this network also, this same 255.255.255.192 is the subnet mask. So if you observe this, the networks which are having same sizes will get the same subnet mask, and the networks which are having different sizes will get the different subnet mask. Since for this subnetting we are getting variable length subnet masking, it is also called as VLSM, variable length subnet masking. Whenever the subnet sizes are different, the subnet mask sizes will be different, and therefore they will be called VLSM, variable length subnet masking. Okay, so one more thing you should observe here is we are having one bigger network and 2 smaller networks. So whenever the network size is bigger, the subnet mask will be smaller. The reason is, in the subnet mask, number of ones will decide the number of zeros. If number of ones increases, then the network size obviously decreases, or you can even think of it this way. Given a subnet mask, number of zeros will give us the size of the network. So for a bigger network, number of zeros will be more and number of ones will be less, which means the subnet mask will be smaller in the number, right? And for a smaller network, number of zeros will be less and number of ones will be more, therefore subnet mask will be larger in the number, right? So this is one way of getting three subnets. One other way of getting three subnets is, maybe I'll show you this. The same way, first is you can choose one bit, which means that can be 0 here and that can be 1 here. Instead of dividing the one side, you can choose the other side, which means in this 0 side only you can choose the second part, which means 0 0 and 0 1. So in case if you have used this subnet masking, then what is the size of this? 64. Why? 6 bits are remaining in the host ID part, 64. And what is the size of this? 128. Now what is the network ID of this? 200.1.2.0 only. Why? 0 0 followed by all zeros. What is the network ID of this? 200.1.2.64. Why? Because 10 followed by 6 zeros, that is the first IP address. And what about the network ID of this? 200.1.2.128. Okay. And now what about the subnet mask? Subnet mask is we have to put all zeros in the network ID part, and then wherever in the subnet ID part you have to put all ones in the network ID part and all ones in the subnet ID part. So in this network we already know that 24 bits have to be ones, which means 255.255.255. We have chosen 2 bits from the host ID part for the subnet ID. Therefore if I choose 2 bits, it is going to be 128 plus 64, which is 192. Even for this network it is same. What is it? 255.255.255.192. And what about this? For this network only 1 bit is chosen for subnet ID part, therefore subnet mask is going to be 255.255.255.128. Therefore these are the network IDs and host ID part. These are network IDs and subnet mask. If you look at both the examples, both are right. So given any question that if they are asking you to divide them into 3 subnets of unequal sizes, you can either do it this way or this way, both are fine. Okay, so we are going to get 2 kinds of answers here. Now how does the routing table? So let's say we are following the division as shown in this example here, right? Then what about the subnet mask or routing table of the internal router? So routing table should contain, one is network ID, subnet mask and interface, right? So this is what, which means we have now 3 networks, 1 2 3, and the router which is connecting all 3 networks. Okay, this is the network and this is the external router, right? So what is the network ID, subnet mask of each one is? Network ID of this network is 200.1.2. of this first network is 0, and the subnet mask is 255.255.255.128, and let us say interface is A. And the network ID of the second network is 200.1.2.128, and the subnet mask is 255.255.255. You can know the subnet mask, which is 192. The reason is 2 bits are chosen here. And the third one is 200.1.2.192 is the network ID, and the subnet mask is 255.255.255.192. let us say B and C. And again you will have one more entry, which is default entry, which is 0.0.0.0, right? And the default entry, let us say, is D. So now in this routing table, if you look at it, now we are going to have variable subnet mask, which means subnet mask is of variable length, right? So again the rules are same. First you take the network ID, the destination IP address, and it with the subnet mask, and if it matches with the network ID, then you send it over that interface, whatever interface is connected. If there are two matches, in this case, whatever is the longest match, see in these three, the longest subnet mask is 255.255.192. Therefore, the longest one is going to get the highest priority. If there are two matches, go for the longest one. If there is only one match, go for it. If there is no match, go for the default entry. Right. So this is also called as variable length subnet masking. We shall see more examples on this. So let's see what could be derived from a subnet mask. Given the subnet mask 255.255.255.192, what do you understand from it? First thing is you should know how many ones are there and how many zeros are there, so that you will understand what is the network ID part, subnet ID part, and host ID part, right? So first thing is you should identify how many ones are there. 1 2 3 4 5 6 7 8 for this one, and again 1 2 3 4 5 6 7 8 for the second one, and again for the third one 1 2 3 4 5 6 7 8, right? And for 192 it is 1 1 followed by 1 2 3 4 5 6. Yes, so this is the subnet mask in binary, right? Now what can you understand from it? So there are how many ones? There are nearly 24 plus 2, which is 26. There are nearly 26 ones, and how many zeros? 6 zeros are there, right? Therefore total number of ones is 26, and total number of zeros is 6, right? So what does ones indicate? Coming to this subnet mask is always ones indicate network ID part plus subnet ID part. And what does zeros indicate is always zeros indicate host ID part. Therefore one thing you can be very sure is, given a subnet mask, depending on the number of zeros, we can say how many number of IP addresses are there in each subnet if this subnet mask has been used to form the subnets, which means from this we can directly say that 2 power 6, which is nothing but 64 IP addresses are present in every subnet. So that is what we could definitely derive. 2 power 6, which is nothing but 64 IP addresses are present per subnet because of this subnet mask, right? And now coming to this 26 ones, they contain two parts. One is network ID part and other is subnet ID part. If I know the subnet ID part, I can say the number of subnets, but in order to know the subnet ID part, I should know the network ID part, right? Therefore if you have to find out how many, see this, we can directly find out the size of the subnet using just the zeros, right? Now if you want to find out even the number of subnets present or number of subnets formed by this subnetting, you have to find out this SID part. In order to find out this SID part, we know that SID part plus NID part is 26, but now we have to find out what is this SID part, right? That depends on what is the network ID part. That depends on what is the class which has been divided into subnets. In case if this would have been class A, if a class A network would have been partition, and if this is the resulting subnet mask, then in that case network ID part is 8 bits plus subnet ID part, that equal to 26. Therefore in that case subnet ID part is going to be 18 bits, right? So in this case number of subnets we got is 2 power 18. Let us say it is said that the network which has been subnetted is a network of type class B. In that case then class B contains network ID of 16 bits plus subnet ID part is equal to 26. In this case subnet ID is equal to 10 bits. Therefore number of subnets possible is 2 power 10 in this case, right? Let us say it is class C network. In case if it is a class C network which has been subnetted, then in that case network ID part plus subnet ID part is equal to 26 bits, and network ID part we already know that it is 24, and the subnet ID part we will find it now equal to 26. Therefore subnet ID part equal to 2 bits. Therefore number of subnets equal to 2 power 2, that is 4, right? So that is how we can find it out. So given a subnet mask alone, we will not be able to find out how many subnets are present, but we will definitely be able to find out what is the size of this subnet, or how many ever subnets are there, what is the size of each one, but then we will not be able to find out number of subnets. In order to find out number of subnets also, you should be given what is the network ID part. Given the network ID part and the number of ones, we can derive subnet ID part. For example, if they say that network ID part is a class A network, then we can derive that it is 8 bits is network ID. So we could do it easily, right? Fine, I'll give you some more examples about this subnet mask. And before going to that, one thing you have to note here is sometimes when I say that subnet ID part is 3 bits, how many subnets are possible? 2 power 3, which is nothing but 8. But there has been some confusion about whether it should be 2 power 3 minus 2 or directly 2 power 3. So both are possible. Previously they didn't used to allow all zeros and all ones in the subnet ID part, which means they didn't used to use the 2 subnets, but currently they are using all the subnets. Therefore in even in Cisco routers there is a command called subnet 0. Using that command we can use all the subnets, which means if we have 3 bits in the subnet ID field, we can use all the 8 bits. That is one thing. And second thing is any valid subnet or any practically used subnet mask will contain a run of ones, which means a sequence of ones followed by a sequence of zeros. That is always there in any practical subnet mask. Any practical subnet mask will contain all ones followed by all zeros. But then theoretically it is possible that instead of choosing the subnet ID part from the beginning, from the leading bits, they are sometimes choosing from any part, which means even though practically we are never going to use any random bits, we are always going to use the leading bits for the subnet ID part. Theoretically there have been some questions like this. They are asking some question like this: 255.255.255.15, that is the subnet mask. Then how many subnets are possible if it is class C? Then count the number of ones: 8 ones, 8 ones, 8 ones, and 15 is nothing but 4 ones, right? So what is the total number of ones? It is 24 plus 4, 28. Therefore network ID part plus subnet ID part is equal to 28, and already we know that network ID part in class C is 24. Therefore subnet ID part is equal to 4. So number of subnets possible is 2 power 4, which is 16. But then if you look at the subnet mask, the last one, this is nothing but 0001111, which is actually not a practically used subnet mask, but theoretically you could use it. The reason what happens, why we should not take the bits from the least significant bits is, why we should always take the bits from the leading factor is, if you take the bits from the least significant bits for subnet ID, we will not be able to divide the network into ranges. For example, see this: if I want to divide the subnet into 2 parts, this one 200.1.2.0 is a network. I want to divide it into 2 parts. How many bits do I need? 1 bit from the host ID part, right? So from the 8 bits I need 1 bit, and that 1 bit can be 0 here, and that 1 bit could be 1 here. If I use this kind of leading bit for subnet ID part, then the range of IP addresses here will be 0 to 127, and here it will be 182 to 128 to 255. In case if you have chosen the subnet ID part to be the leading bit. In case instead of using this leading bit, if you have used the least significant bit for the subnet ID part, then what happens is, the least significant bit whichever is 0 falls in this subnet, and the least significant bit whichever is 1 falls in this, which means 0 falls in this subnet and 1 falls here. All the even numbers will fall here: 2, 3, 4, 5, 6, 7. So that is why we generally don't use such any gaps in the subnet mask in practice. So in theory, there have been questions asking about what if this kind of thing is a subnet mask. You could derive the answer, but then we are never going to use them practically. So practically, always a subnet mask is going to be a run of ones followed by a run of zeros, right? So we shall see more examples on how to use this, how to derive more information from subnet mask. Okay.